start. So let's go ahead with the second lecture from Fabio. Please.
Okay, can you hear me? Okay, good. Well, thank you again for this opportunity. So the lecture of today will be a sort of mirror of yesterday, but it will be about 5D superconformal field theories, and in particular construction of 5D superconformal field theories from type 2B. From type 2B 5 and 7 brane webs. So this is a natural framework in order to actually fit holographic setup, as I will explain later. So my lecture will be based on this set of references. So I won't indicate every time these references in the note, as I didn't do yesterday as well. But basically, this is the core of my lecture. So where I got the material I'm going to talk about. And I also indicate other references if they're relevant later on. So the plan of this second lecture is the following. So I'm going to briefly give an introduction about 5D gauge theories, and actually I have to thank Ifan for briefly introducing to 5D gauge theories. And also I will talk about then the web construction with 5 branes. I will again see how these branes can be this brane setup can be manipulated. I will talk about the holographic limit of these brane webs, and finally I will describe some computation that one can do with holography. So let me start with an introduction. As Ifan already mentioned, the important thing, one of the important facts of 5D superconformal field theories, and in general of theories in more than 4 dimensions, is that there is no Lagrangian at all energy scales. And the best thing that we can do is to have a Lagrangian at low energy, which is an effective description in the infrared. And this Lagrangian can be an effective description of something non-trivial in the UV. So for example, we can have a UV CFT, and in 5D, we can deform this UV 5D CFT to go to an infrared description. And the infrared description can be a 5-dimensional gauge theory. So the deformation will look like this. So an operator with the coupling. And at low energy, this deformation is basically the following. If we want to have a gauge theory description in infrared. So this presentation of the deformation is only valid at low energy. But at high energy, it might look something like this with an operator of the CFT. And moreover, the low energy description is a non-renormalizable theory because the coupling, the expansion and the perturbative expansion comes with this parameter. So let me give you some comments. As already mentioned, in 6 dimensions, the superconformal algebra does not allow for mass deformation. And this is different in 5 dimensions, because in 5 dimensions, the superconformal algebra actually allows for mass deformation. So in this case, this can be a parameter, which is different from 6D. Okay, so let's start from a brief introduction about n=1 gauge theories in 5 dimensions. So if we have an n=1 gauge theory, we have a gauge group, or an algebra, or a Lie algebra, which has rank R. And in order to derive the massless spectrum, a convenient way is to label it by the S of 3 subgroup of S of 1, 4. And this representation are labeled by 1 spin. So for example, we can have a vector multiplet, massless vector multiplet, which comes with this spin representation. So we have 2 fermions, a scalar and a vector. So the vector is in the adjoint, and the scalar takes value in the Cartan of the gauge of the algebra. And moreover, these fermion they have an index I because they transform under the SU2R symmetry. So n=1 gauge theory also have an SU2R symmetry. Moreover, we can have also matter hypermultiplets, and matter hypermultiplets come with 4 scalar plus, so spin 0 under the SO3, and plus 2, 1 alpha again. And again, these two, the fact that there are two fermions, this tells us that this transform under the SU2R symmetry. So this is basically a summary of wherever the content of field transform under the gauge Lie algebra or under the SU2R symmetry. Okay, as already mentioned by Ethan, we can have a Coulomb branch if we give VEV to the vector multiplet scalar. So in 6D we don't have vector multiplet scalar, but in 5D we do have vector multiplet scalar. For example, a way to understand this is by reducing a 6D vector multiplet on a circle. Then what you get is a 5D vector multiplet, and the scalar will be related to the vector in the circle direction. So in 5D we have this Coulomb branch, and the Coulomb branch tells that the VEV of this is different from 0. And moreover, the gauge group is broken to U1 to the power of the rank. And in this Coulomb branch, we have a quantity which is a real quantity, a real function of these VEVs, and it's called the prepotential. So this is the prepotential. And the prepotential, as Ethan said, it's a cubic function of this phi in general. So if we have a gauge group, for example, C is the Cartan of the Lie algebra, then AI, alpha I are the roots of the gauge algebra, K is the classical Chern-Simons level, and Dij is this trace of the fundamental these are the generator of the gauge of the Lie algebra. Moreover, if we have some hypermultiplet in some representation of the gauge group, we have to. So this is the contribution to the prepotential, and these are the weights, and so these are the flavor representation. So if we have hypermultiplets, then they will transfer. So these are the weights with respect to the gauge Lie algebra, and these are the representation with respect to a flavor symmetry. So in case we have a flavor symmetry rotating the hypermultiplets, we have to sum over this flavor symmetry as well. So moreover, how this effective prepotential regulates the dynamics of the theory of the Coulomb branch theory is, well, it gives an effective Lagrangian in the following terms. So we have Gij, and Gij is basically the second derivative of the prepotential. So this is the coupling of the kinetic terms in the Coulomb branch. And moreover, we have also this term, this effective Chern-Simons coupling, which is the third derivative of the prepotential with respect to the Coulomb branch parameter. So this determines that this effective dynamic in the effective dynamics in the Coulomb branch. So a necessary condition in this Coulomb branch, in order to have a CFT, is whether we can actually get rid of this this gauge kinetic term by sending the coupling to infinity. So a very strong coupling. So this is a So this is a condition, and it's a condition in order to have a CFT in the UV. So is the Coulomb branch, is this limit allowed in the Coulomb branch? That's the question we need to ask. So in the Coulomb branch can be pictorially seen as follows. So for example, we have, it can be seen as a cone, so which depend on phi, but also depend on some mass parameter. So if, for example, if we allow this mass parameter to vary, so if we like think about them as being dynamics, then this is called the extended Coulomb branch. And the group of this extended Coulomb branch is basically the gauge group plus the classical flavor symmetry. But if we fix the mass, this will give the Coulomb branch, the Coulomb branch in terms of the phis. And the Coulomb branch in terms of the phis is regulated by this prepotential via these couplings. So this is just to tell you that there exists a more general quantity with respect to the prepotential, which is called a more general Coulomb branch, which is this extended Coulomb branch, which also takes into account about this mass parameter. Okay, but what is the definition of the physical Coulomb branch? So the definition of the physical Coulomb branch is the following. So first of all, we want that the metric stays positive. So that this is the metric, the gauge, the kinetic term in the Coulomb branch. And secondly, we want that this quantity also stays positive. So this quantity, we need to impose this because otherwise there will be states which becomes, so when this quantity changes sign, we will have states which become, I will tell you what these states are in a second, but if this quantity changes sign, we will have states that become light. And when these states become light, the gauge theory is not really a good description at that in that regime. So this is why the physical Coulomb branch of the gauge theory needs to be to take this into account as well. So what is generically the BPS spectrum? The BPS spectrum of a 5D gauge theory is then given by electrically charged particles. It's also given by instantons. I will explain a little bit about instantons in a second, but it's also given by monopole strings. So in 5D, there were those BPS strings, which they have electric and magnetic charge, but in 5D, there are only monopole strings. So going back to the instantons, so the instantons are the following configuration. So if we take a point like instantons in 5 dimensions, this point like instanton will be surrounded by an S4. So this S4 is taken in the R in the space-time R5. And this instanton has a charge given by this. So if we have a field strength for a gauge theory, F, we can integrate this quantity, this is instanton density, on the S4. And this will give a number which is called the instanton charge. So moreover, there is, associated with this instanton charge, there is a current, which is given by the odge of this density. And this is called the topological current. And gives a global symmetry of the gauge theory. So for a given gauge theory, we have, in this case, we have a U1 topological current. So if we have a particle, generically a particle in 5D, then this particle has a mass, and if it's BPS, this mass is equivalent to the central charge. And the mass is equal to the electric charge multiplied by phi plus I, this is the instanton charge, multiplied by m0, where m0 is equal to 1 over G m squared. And 5 is the Coulomb Branch parameter. Moreover, we can have monopole strings, and the monopole strings, their tension is equal to n, so magnetic charge times the first derivative of 5i. And so this is where this first derivative appears. So when this first derivative is 0, it means that the some strings become light. And this is why, in order to have a good gauge theory description, we wanted to impose these conditions as well. Okay, so any questions so far? Yeah, there is a relation. So the question is there any relation between Chern-Simons level K and effective Chern-Simons levelCijk? Yeah, there is. And the relation is given by the third derivative of this. So if you derive 3 times, you will get a contribution from K, but you can also get a contribution from this, which corrects the bare Chern-Simons level. So this Cij will contain this K, plus some correction, plus some loop correction, which is given by this term. Okay, so let me start with the 2B webs. So the main ingredient of the 2B web is given by PQ fibranes in 2B. So what are, let me start by like standard fibranes. So the standard fibranes in 2B are NS fibranes, and they fill this direction. And then we have D fibranes, which fill this other direction. So the NS fibranes are orthogonal to D fibranes in this case. But we can also have more general configuration. And this more general configuration have like a sort of angle in this plane 5 and 6 plane. And this angle is given by this condition. Moreover, we can also have PQ7 branes in the system. And the PQ7 branes are point-like in the 5th or 6th direction. And they fill the 7, 8, and 9 directions. So, for example, we can try to find a back-reacted solution of type 2B of this brane system, but that might look complicated. So one strategy we can take is we can study the calibration of these branes. In a sense, we can study the projectors of so we can study the spinor equation and how much supersymmetry of the 32 supersymmetry of type 2B this configuration preserved. So for example, if we take an NS5 brane and if we take a D5 brane, the projector will look like this. So we have, these are the gamma matrices, 10-dimensional gamma matrices. For NS5 we have the 5th direction, and for D5 we have the 6th direction. And what this implies, if one write down the components of this spinor, the 32 components of these spinors, as well as the gamma matrices, imply that 8 supercharges are preserved by this configuration. And the physics of this configuration is actually encoded in the 5 and 6 plane. So these are the two directions, these two directions. So this is what encodes the physics. So there will be also non-trivial information given by this direction. For example, the R symmetry is the 10-dimensional isometry, the subgroup of a 10-dimensional isometry which rotates this free direction. In this case, it's SO3, so which is consistent with the SU2 R symmetry. And moreover, the physics, so the theory is 5-dimensional because these brane have in common 5 dimensions. So this part of the Lorentz, the 10-dimensional Lorentz symmetry is preserved. In 2B, we have another symmetry, which is SL 2Z, and this symmetry acts on the 5 and 5 on the 5-6 plane. For example, it can act on the PQ charges, where the PQ charges are the charges of the charges of the 5 branes in this way. Well, this is an SL2Z matrix, for example. Okay, so we have this configuration of NS5 and D5, which is it has 8 supercharges, so 8 supercharges are preserved. And the naive configuration we can have is the following. So we have an D5 going into an NS5. So in order to analyze this configuration, we can take the Bohr volume theory of the NS5, and it X6, so the 6th direction, is a scalar on the Bohr volume of the NS5. So it's a scalar, so it's the orthogonal direction of NS5, so it's a scalar in the Bohr volume theory of NS5. And there is, if you write down from the brane action the equation of motion by varying with respect to X6, and X6 that can depend on X5, can depend on the coordinate of the NS5. The equation that one gets is the following one. So this is the classical equation of motion. And how do we solve this equation of motion? Well, the solution is the following. So X6 is equal to 1/2 X5 plus X5. And we can see that for X5, very small, we can recover the NS5 branes because X6 is equal to 0. Very small and negative. We can recover the the NS5 brane. So which is consistent with this limit of going down here. But for X5 big, what we have is that the configuration gets distorted, and the solution for X5 big is this one, X6 equal X5. So this would be a solution for a 1,1 brane. So we have this configuration. So a 1,0 brane, which meets a 0,1 brane, will give rise to a 1,1 brane. So this is a naive configuration. And this is the actual configuration. But one might wonder whether this configuration breaks supersymmetry. It actually doesn't break supersymmetry. But in general, one needs to satisfy a sort of charge conservation. So you remember yesterday that I explained the charge conservation around the NS5 branes for D6 brane coming in and coming out. Here, the story is very similar. So we can pick an S4 surrounding this junction. And now we need to impose charge conservation of the F3 flux around this F4. So the F3 can be written in, so it has an H, which is dV2, and F3, which is dC2. And this is like a complexified combination. Okay, so we can compute these charges. So we surround this junction by this S4, and now we take the radius of this S4 fairly big. So we take this limit, and in this limit, the dF3 is proportional to this quantity. So this is the volume of F4, so the volume form of an S4, and it would be multiplied by the QI and PI coefficient in this way. But for consistency, we need that this, so the Bianchi identity will tell us that in general, this is equal to 0. So this is the condition. We need that the sum of the integrated Bianchi identity should vanish, and this will imply that the sum over Pi equal to the sum over Qi equal to 0, which what happened in this configuration. So the sum of the charges they vanish. Okay, so this is a simple configuration. Any questions so far for this? So we can further complicate this simple configuration by starting connecting various junctions. And for example, by adding more vertices, so by adding more of these junctions, we can model the Coulomb branch of a gauge theory. So in this case, we have 4 junctions, and these 4 junctions, they all respect this junction quantization. So this will be 1, 1, going to 0, 1, and 1, 0. Similar here, similar there, similar there. So this, the charge conservation is satisfied. Moreover, how this web actually engineers the gauge theory? Well, the number, first of all, the number of finite size facets is equivalent to the rank of the Coulomb branch. Moreover, the D5 brane word volume theory will give a gauge theory. So so yesterday I showed you that by expanding the DBI plus Western interaction of the D6 brane into small alpha prime, then you get a gauge theory. Similar for the D5 brane, you can get a gauge theory. But separated D5, so we can, since we have a further extra dimension in this web with respect to the 60 brane configuration, in this case, we can separate the D5 brane, and every D5 brane, so every separate D5 brane will give a Cartan U1 gauge. Moreover, the strings, the F1 strings, so the D5 brane by tuple cancellation are connected by F1 strings, and the F1 strings will correspond to the W bosons. And in particular, when the D5 brane are separated, the W bosons are massive. So they have a mass, which actually depends on the rev. Moreover, let me comment that in this case as well, one of the U1 in general, if we have a system like D5, parallel D5, one of the U1 will be decoupled, and will be decoupled by also similar like a Stuckeberg mechanism, similar to 260 for the 6 branes. Moreover, we can have D1 branes stretching between NS5. So what are these D1 branes stretching between NS5? Well, these D1 branes are just instanton. In this case, one instant. So this will be an instanton. And now we can compute the masses of this particle. And we can compute the masses of this particle by computing the length on the string on these webs. So the length of the string is also can be expressed in terms of this BPS formula. So where the mass is equal to the electric charge multiplied by 5, the instanton charge multiplied by m0, and a flavor charge, if there is a flavor rotating hypermultiplets, multiplying the mass of the hypermultiplets. So and this is equivalent to the central charge. So in this case, we don't have any flavor hypermultiplet, so which I will discuss in a second. But in this case, so we don't have flavor. We still have like electric charge and instanton charge. So the W bosons, the mass of the W bosons is just 5. Whereas the mass of the instanton part, so in this case, I equals 0. And whereas the mass of the instanton particle is given by 5 plus m0. Where m0 is 1 over g m squared. So again, this can be computed by measuring the length of this segment. And we see that there is an m0 and there is a phi, which is given by this plus this. So I equal 1 in this case. Okay, so what happens if we add matter hypermultiplets? Well, for example, the matter hypermultiplets can arise from the following web. So down we have like a new segment in this web. Again, on each junction, the quantization, the charge conservation is satisfied. So we can have this extra leg in the web. And what are the masses hypermultiple in this case? Well, what are the hypermultiple in this case? And what are their masses in particular? So we can compute. So the first quark will be given by strings stretching between these two D5. So the first D5 with this semi-infinite D5. And if we compute the mass, so by computing the mass, I mean computing the length of this segment, these give the following number. So this is this means that there is an electric charge, which is 1/2, and also a flavor charge, which in this case is equal to 1. But it's more difficult actually to detect the other quark, which will form the hyper. And the other quark is given by, it can actually be detected by this bound state. So this is a bound state of F1, D1 with this 1,1 string. And the mass of this bound state is given by the following. So this is 3α5 plus. So this is given by just computing the length of that bound state. And 0. And we can see that I is equal to 1, and E is equal to 3α, and F is equal to 1. So QF is equal to 1. And so we can see that this bound state is given by 3 part. So this one, but there is also this other part. And this other part will be the other quark. Fine. So this will give rise to the hypermultiplet. Okay, so we can then, okay, let me actually comment on a couple of things. So this is, as I told you, the mass of the hypermultiplet, which is the distance, the length of this segment. But there is also another quantity, which is the bare mass of the hypermultiplet. And the bare mass will be equal to the distance of the D-fibrane from the vertical distance of the D-fibrane from the origin of our web. So this it's like the bare mass of the hypermultiplet, so this quantity. And the quark then has the actual mass of the quark is given by this. So there is also a flop phase, and it's in order to see whether this hyper can become massless, this flop, which is the following operation. The following operation on the web. So we change the direction of this segment. By doing this, we get this new web. So we change the direction. So we shrink this to 0, and then we open up in this direction, as is done here. So in this process, the mass of the hypermultiplet changed sign, and in this transition, so there is a point in this transition where, since this changed sign, where the hyper becomes massless. Moreover, we can, as I anticipated, we can have monopole strings. And monopole strings are given by D-free brane extended on the finite size facets of the web. And their tension is actually computed by the.
So there is a question in the chat from Federico Carta. Why having two quarks of different mass inside the same hyper doesn't break SUSY?
It's not different. I mean, the electric charge is different. But that's usually what should be for an hyper. So you have the representation, and it's only get representation. I mean, yeah. So the mass is this pair mass, if you want, and this is the same for an hyper. So this one, which is this length. But this just tells you that the electric charge is different between the two quarks. Okay, so the monopole strings are given by D3, and D3, the tension of this D3 is given by the area. The area of this D3, like which wraps the finite size facets. Moreover, we can have we can compute the prepotential, and to compute the prepotential from the web, there is a simple formula. If you compute the area so the tension of these monopole strings, so the area of the D3 wrapping finite size facets, then you can compute the prepotential. And the prepotential will be given by just this integral. So where I integrate the area of in terms of phi. So in this case, this can shift by constant term, but the constant term will actually not affect the derivative of the prepotential in terms of the dynamical Coulomb branch parameters. So the prepotential will not actually change by shifting this. Just I mean, the prepotential, which is a functional in terms of the dynamical parameter, will not change. Because what the physical quantity are really the derivative of this prepotential with respect of dynamical of the dynamical parameters. Okay, so but what are the other brain manipulation that we can do by using these webs? So we have seen this already, but just to repeat, so we have this configuration. This configuration is this, for example, the intersection of these. The junction of this brane with these charges. So it has a conserved, so the consistent condition is satisfied at this point. And this would be the strongly coupled. The strongly coupled theory. So the CFT. So there is no scale here going on, and everything is like finite or infinite. So there is this evidence that there is a CFT. And so nice that if we actually we can deform this by adding d5 branes in this case, and this deformation will be actually given by this, and M0 now is the coupling of the gauge theory. So this is the gauge theory. This is the gauge theory where all the matter is massless. Finally, we can also move into the Coulomb branch. And by moving into the Coulomb branch means that we are also resolving the other direction. So which in this case is the vertical direction. So we give VEV to 5, and the VEV to 5 means that the gauge theory now is broken and we're going into the Coulomb branch. So this is the first brane manipulation that we can do. So we can see here that from the web that we actually have mass deformation. And this is different from 6D. And in fact, this is a nice consequence of the fact that we have a web in this case. So in 6D, we have only a linear configuration of brane. So we can only move in the 6th direction. So the strings that, for example, will give rise to hypermultiplet, they are stuck in the 6th direction. But in this case, they can actually move in another direction. And you can associate this indeed to, so in this other direction, you can associate this to actually mass parameters. So this is consistent with the result that in 5D, in the 5D superconformal field theory, you can have mass deformation, whereas in 6D, there are no mass deformation. Finally, there can be cases where a gauge theory is not available. So for example, if we have a junction of -2, 1, 1, 1, and 1, -2, so this is okay. And we can still resolve. So we can still open up this configuration. And by opening up, we get this other configuration. But this other configuration doesn't have a gauge theory interpretation. So it doesn't have like parallel D5. So but we can still associate a Coulomb branch with this theory. So there is no gauge theory, but there is a Coulomb branch. So any question on this?
So you have a question in the chat. So how to distinguish conifold singularity and conformal limit of SU2?
Well, the conifold singularity right, so the conifold singularity is just, right, it's different. So the conifold, so the SU2 is this, is the intersection of -1, 1, 1, 1, -1, -1, and 1, -1. Whereas the conifold singularity will be the intersection. Why the grid, I will actually talk about this in a more general setup, but the grid with 1 D5 intersecting 1 S5. So and this doesn't have a Coulomb branch because it doesn't have a, so you resolve once and this is already defined. Whereas this you can resolve more times because you have multiple branes. So for example, in order to separate, so when you separate this from this, you get 2 NS5 branes. And the fact that you have 2 NS5 branes, then you can resolve in this direction and get the Coulomb branch. Whereas here, you can separate a 1, 1, 0 with the 0, 1 with the 1, 1 brane. And that's already fine. So you don't have multiple D5. So, okay, let me actually talk about a slightly more complicated example. So let's take SU3 gauge theory with bare Chern-Simons coupling. So classical Chern-Simons level equals 0 and 4 flavor. So this configuration, actually, so if we start, well, we can start with this configuration. This will be the CFT. So the strongly coupled limit. And the finite coupling limit it means that we separate these free branes, so these free PQ branes from these other free PQ branes. So we separate in this direction, and what we create are free D5 branes here. Moreover, in this case, there are also 7 branes. So on any semi-infinite D5 branes, so semi-infinite D5 branes which go to infinity, so semi-infinite D5 branes will correspond to flavor symmetry, to the classical flavor symmetry of the gauge theory. And in this case, we can actually end it on a 7 brane. So PQ5 brane can end on a PQ7 brane. And in this case, we see that there are 2, so there is 1, and so there are multiple D7 brane. So we can end a D7 brane on a semi-infinite PQ5 brane in this way. So it doesn't, in this case, for example, in this configuration, it doesn't matter if you substitute this with semi-infinite legs, which go to infinity, or 2 legs which go to infinity here, 2 legs which go to infinity there. It's just convenient to have 7 branes for what I'm going to tell you in a second. So we can resolve in the Coulomb branch. So we do this gauge theory, and then from this gauge theory, we move in the Coulomb branch by resolving in this vertical direction. So we give VEV to phi1 and phi2. So in this case, it's a rank 2 theory. And this web actually engineers the Coulomb branch of this SU3 gauge theory. So the floor flavors are indeed given by the 2 5 branes ending on 7 brane. So this one on the left, and same on the right. So we have 2 here and 2 there. So this 7 brane can go to infinity. So we'll have 2 semi-infinite legs of the 5 branes, and these 2 semi-infinite legs on the right and on the left will correspond to the 4 flavors. So in this case, the 4th flavor, the flavor which would be U and F in this case. In this case, we have NF equal 4, so U4. Since we have these 2 brane on the left and 2 brane on the right, the subgroup that we explicitly see is just U2 times U2. But the full flavor symmetry is really U4. Okay, but given this web, now we can, and let's stay with this configuration for a second. So where we have the gauge theory and the massless matter. So we can do some X-branch deformation. The X-branch deformation from the web is defined as follows. So we can move subwebs, consistent subwebs. So for example, let's take this example 1. So consistent subwebs are, for example, this one. So the red one, or the light blue one, or this dark blue one as well. Or there is another consistent subweb, which is this D5 connecting to a D5. So consistent means that if there is a junction, the charge, the charge constraint is satisfied. And we can move this web in the 7, 8, 9 direction. So so the 7 brane would be fixed, so they don't move, but we can move this consistent subweb along this 7, 8, 9 direction. And this actually means that we are giving VEV to certain operator. This operator will be given by strings connecting these subwebs. And the oscillation of these strings will give rise to this in the 7, 8, 9 direction, which is the direction filled by the 7 brane, will give rise to this operator. So for example, in this case, we're giving VEV to some baryonic operator. So in this case, let me schematically indicate this as determinant of some hypermultiplet. So the hypermultiplet transforming the SU3 gauge groups times the U4 flavor symmetry. And in this case, the theory is X to U1 square. So the SU3 is X to U1 square. We can we can separate these subwebs also in another way, in this way. So we have this purple subweb given by this one. And then we have this other subweb given by the 5 branes stretched between the 7 branes, and then we have also this one. And this corresponds, so if we separate this web along the 7, 8, and 9 direction, we give VEV to mesonic operator. So mesonic operator can be like a contraction of the left hypermultiplet transforming into U2 times SU3 with the right hypermultiplet transforming in the we sum over the gauge. So we want the gauge invariant operator in this left. Which one? In this case, the theory is equal to SU2 times U1. Finally, we can also give VAV to both operators, so the bosonic operators and the baryonic operators. And also this will be part of the X branch, and the theory in this case is also X to U1 squared.
Fabio?
Yeah.
What exactly happens to the asymmetry in this case? So if you're going into 7, 8, 9 directions, then you're breaking the asymmetry completely or like partially?
I mean, you're spontaneously breaking the asymmetry.
Okay. To U1, or because you can, if you only penetrate one direction, you would naively think that you retain some U1.
Yeah, in general, you can penetrate one direction, and yeah, you can. But suppose that then you send one subweb to infinity, and the web that you're left over is consistent, then you restore like SU2. It's similar to the segment.
Yeah.
Similar
you have
to
some local SU2 asymmetry, and then.
I mean, the SU2 asymmetry is broken when the distance is finite, and then when it's infinite, it emerges again.
Okay, yeah.
Thanks. So, for example, you can move from one theory to the other theory by sending this subweb to infinity, and then in the theory that you get after, so you get after this flow triggered by these operators, it has an SU2 asymmetry. But in the meantime, the SU2 asymmetry is spontaneously broken. And I think, right, it's to U1 because you can just pick one direction. Okay, but can you? Probably it's frozen. Let me share it again.
I mean,
we can see the cursor, but not the pointer.
Right.
Yeah, it was frozen. Let me share it again. We can also have some Coulomb mix branch. And for example, we can resolve in this vertical direction to get in the Coulomb branch. And in this case, you can see we can separate this subweb. So this D5 brain connect these 7 brains in the 7, 8 dimension. This will correspond to giving back to some mesons, but now in the Coulomb branch. So the general picture that we have is the following. So we have a Coulomb branch. We have an origin of the Coulomb branch, where at the origin, the superconformal point lies, or the strongly coupled point lies. And then at this point, like new direction, new moduli space open up. This is the X branch moduli space. So as we've seen from these webs. So there is a baryonic branch, there is a mesonic branch, there is an overlapping branch. So these were the 3 cases that I show you. So there can be this structure. And then there is also a mixed branch, where the mixed branch is given by this one. Okay, there are other moves that we can do. So other like transition, other like manipulation of this web. And one move is, again, this Anonymity move. So being a 2T dual version of the 3-dimensional Anonymity system, we can do an Anonymity move also here. For example, if we have a 7 brain and we want to move this 7 brain across this junction, what this results is that these two 0-1 brain, they become 1-0 brain, and this brain has crossed on the other side. So there is a sort of annihilation and then creation of 7 brain, or like 5 brain connecting the 7 brain if you want. And moreover, so an Anonymity transition plus SL2 transformation, they can define different webs. So we can do an Anonymity transformation and then the web will change. Or we can do an SL2 transformation, for example, an NS duality transformation. NS duality here, I mean a rotation of this web of 90 degrees. So this one corresponds to SU3 with 2 flavors. And the rotation one corresponds to SU2 times SU2 quiver, connected by some bifundamental hypermultiplet. The bifundamental hypermultiplet are now given by these. So you can detect this fundamental hypermultiplet, bifundamental hypermultiplet by this finite segment, and in particular by strings connecting this D5 with this D5 and this D5 with this D5. So this is SU2, SU2 quiver. And they are dual by S duality in terms of the web. So apparently this will define very different gauge theory. But if one writes down the Coulomb branch, realizes that the Coulomb branch has a sort of overlapping region, which is different, which is not trivial. But what is important here is that when you shrink this web to the strongly coupled point, the physics of that strongly coupled point has not changed by doing this SL2Z transformation. So the strongly coupled point would be actually the same of if you start from this description or if you start from this description. So this, in other words, this would be two different IR descriptions of the same UV fixed point. And the fact that they have the fixed point, so that the shrinking of this web is the same, basically in these two cases, it's a good evidence that these two descriptions are dual. Duality means that they are just different descriptions of the same UV CFD. Okay, let me tell you about one slightly more complicated configuration. So we can take the grid. So as answering to the question before, I introduced this grid, which is 1n5 brane intersecting 1ns5 brane. But we can take more branes intersecting in this way. This will be a consistent configuration. But we can also, so since we have semi-infinite D5 and S5 brane, we can end 7 brane on this semi-infinite D5 brane in this way. So we can end D7 brane on this semi-infinite D5 brane, or we can end 0, 1, 7 branes or on these NS5 branes. And then we can also study so we can also resolve this web by separating the brane. And by separating the brane, what we get is a gauge theory description, which in this case is an SUN linear quiver with M, with 2 and SUN flavor, and with M bifundamental hypermultiplets. So we can see, we can zoom here, and we can see, so these, I mean, here I draw these as separated, but they're not actually separated. This D5 brane, they really collapse on each other. What this means is that we have a situation like the following one. So there are 4 branes, 3 branes, 2 branes, 2 D5 branes, and 1 brane here. So there is 1 crossing, there is 2 crossing here, there is 3 crossing there. And now we can do like in 60. We can move the 5 segments along the 7 branes on the 7, 8, 9 direction. These are consistent subwebs. So it's basically, it's like accessing the X branch for this more complicated example. And if we send some of these segments to infinity, well, one configuration that we can get is this one, where 2D5, where KD5, and on a D7. If we now try to understand the Coulomb branch or the gauge theory description of this configuration, we have to separate the brane, but we also need to do some Anonymity Move. So in order to understand this, we need to take the 7 brane and bring the 7 brane inside. Because also in this case, we have more 5 brains hanging on 7 brains. And this is not really, it doesn't have really a standard gauge theory interpretation when we resolve the web in the Coulomb branch. But the fact that we bring the 7 brain, since the 7 brain like source and a monodromy for the axial dilaton, this tells us that there is a monodromy cut on the plane. So the monodromy cut is generated by T, which is a generator of SL2Z, to the n over 2 power. And we see that at this point, the monodromy cut changes this quantization, this condition of the charge conservation condition at this point. And we can read from this configuration the quiver description. So this will be, this D5 brain will give rise to an N SUN gauge theory given by this. So this will be SUN flavor, this SUN gauge theory. There will be fundamental transforming between this and this. So, and in general, we have more SUN until we reach the point where the 7 brain, so the column where the 7 brain are inside, and in the column where the 7 brain are inside, there can be strings connecting the D5 brain, the finite size segment D5 brain, with this 7 brain. So there can be such a string, or such a string, such a string. What this means is that there is fundamental, flavor fundamental hypermultiplets. And so in this case, this corresponds to the SUK flavor symmetry. So here we have K D5 brains. And then there is also the rank changes. So we see that here we have rank 3, and here we have rank 1, and here we have two D7 brains. For example, if we specialize N equal to 4 and K equal to 2 and M equal to 3, you can actually get like an example for this quiver, like a special instance of this quiver, which I leave you as an exercise to specialize this for M equal to 4. So M equal to 3 and M equal to 4. To see that this is consistent with this explicit picture. But the general quiver that you get for general N and M is this one. And this, we can see it's analogous to the X branch that we got in 60, where so there is a quiver which, so the starting quiver was this one, and now we get a quiver where there is a ramp. And this is given by basically, if you activate some nilpotent VEV for operators, which transform under this SUN symmetry. So this is an example of X branch in a more complicated configuration. But X branch generically is indeed defined as moving this subweb, this consistent subweb along the 7 brain directions. And this is just a more non-trivial example. Okay, so let me talk about holography now. So we have defined these webs, and we can ask, is there a, so we can ask whether this web as brain system have a near horizon geometry. And in particular, whether this near horizon geometry will give rise to the ADS6 solution of type 2B. So the general strategy is to solve the SUSY variation of the Gravitino and the Dilatino in type 2B. So this is the general strategy, where we also impose the following ansatz: ADS6 times a word product with M4. And it turns out that this has a lot of solution. And this one was, they were found in a paper by Docker, Perl, Uleman. So this explicit solution. And so these actually look complicated, but they can be it is again a pictorial way to describe this solution. So for example, let's take the grid that we have taught so far, and let's surround the grid with an S4 embedded into the 5, 6, 7, 8, and 9 coordinates. What the brain intersecting, the brain intersecting the S4 will give some sources. And they will basically back react on the geometry. So M4 or S4 will be the form, and will be the form in a sigma times S2, where sigma has the topology of a disk, and S2 is an S2 sphere, which is fiber over sigma. And in order to have a regular solution, we need that the volume of S2 shrinks at the boundary of sigma. Moreover, these sources in the solution, they will be poles. They will be poles in terms of, so poles of some function. So the metric looks like this. So it has a warping factor, well, this is the coordinate of the disk, and this is the S2, which is again warped on the disk. And the F3 is, you can write an F3 as a linear combination of dB2 with I dC2, where this is just dC, and C is a complex function, and tau is this combination. F5 vanishes. So this function, which are the function that specify the solution, they only depend on two holomorphic functions, which are A plus and A minus. And this function, they depend only on W. So we see that also this function now, they only depend on W or W bar. But the A, so these are generically not holomorphic combination of this function, but these two functions are holomorphic. So if we take sigma, sigma will look like this. So it's a disk, and we have some singularity. So this singularity will be pole singularity, pole for this function. And they will come with some data. So in fact, if we compute the fluxes close to this pole, so we can transform, so we can do this transformation. The coordinate is I plus. So this is transformation of coordinate close to the pole, so here. So we have a theta angle, and we have an R direction, which is orthogonal to the pole. And what this implies is that close to the pole, we have this, and I, Pi, C, 2, where vol2, sorry. Vol2 is the two-form volume, the volume form of the two-sphere. And also we have these Ni, Qi, C. So this is basically the volume form of a free sphere. So around these poles, the solution will look like a free sphere with charges. So the flux will have quantized, will be quantized, and the charges, the quantized charge will be given by this. And again, we need this constraint. Okay, so we have described this solution. So these solutions are complicated, but close to the pole, they can have this simple form. And we can actually compute something with this solution. And well, for example, we can compute, again, the linearized spectrum. So the linearized spectrum will be given by the supergravity fields, which are deformed by a term like this. And then if we plug back into the equation of motion on type 2b, what we get is again a sort of Laplace equation. And the Laplace equation is the following one. So we have a Laplace operator on delta super. This is equal to mass square delta super. This is basically the KK spectrum. And the KK spectrum corresponds to certain operators in the dual CFT. So in the dual CFT, we can have operators which are labeled by some quantum number, like the spin inside this algebra. So the spin so this is space-time quantum number. This is the scaling dimension, and this is the R symmetry. And moreover, the mass of so the mass of this configuration, of this classical configuration, corresponds to the scaling dimension by this formula. This is for a scalar. So we can compute operators and we can compute their dimension by using this holographic solution. An alternative approach can be given by the following. So it can be given by looking at probe branes. So if we look at probe branes in this geometry, we can understand certain operators. For example, we can look at, if we take again the grid, which is a simple example, we can take also a more complicated web. We can stretch strings between the semi-infinite brane in this and here. So we can stretch the strings crossing the junction from one side to the other. So these are D1, and we can stretch F1 string crossing the junction in this direction. And in the solution, this will be modeled by D1 connecting two poles and F1 connecting two poles given by NS5, given by D5 branes, whereas the D1 will connect the poles which correspond to NS5 branes. We can resolve this grid. So in this case, it's all collapsed. So this is really a point. But we can resolve by moving consistently, by distancing consistency, by separating consistently the branes. And what we get is a quiver gauge theory. And the quiver gauge theory here was like this linear SUN quiver. So in this quiver, there can be there are operators which are like product of the hypers. So these are long meson operators, which are the product of all these bifundamental hypers. Or they can be baryons operator, and baryons operator are determinant of these hypers. So these are all gauge invariant operators. And moreover, they're not only gauge invariant, but they are protected by half BPS condition, by the shortening condition, as Ethan already mentioned. So these are protected operators, and even if they are operator of the low energy theory, they can be a good operator also on the superconformal point. Of course, they will not have this gauge theory interpretation, but we know that they exist at the superconformal point. We can compute the dimension of this operator from this quiver, and this is given by these numbers. So these you can compute from. So this is 3½ multiplied by n, because you. So this is the large n behavior of these operators of this scaling dimension. And this operator, the scaling dimension of the operator, can be, they correspond via this formula to the mass of the string. And the mass of the string in this background is computed by evaluating the on-shell action on this solution. So you take the on-shell action, so the dBi action plus best domino action of the D1 or F1 brane, and you evaluate on this background. So where this D1 or F1 brane are extended along this direction in this disk. And it turns out that the mass is equivalent to the scalar dimension via this formula. So this is a good test for this set of operators and for this ADS6 CFT5 pair. What we can also compute in 5 dimension is the free energy. So in 60, the free energy was computed by computing this A coefficient. And the A coefficient was a combination of continuous top anomalies. But in 5D, there is no continuous top anomalies, especially in any odd dimension. So the question is what we can do and how we can compute the free energy of the CFT. Well, it has been computed in many papers, but for the grid, especially in this paper, by evaluating the S5 partition function. So if one evaluates the S5 partition function, particularly the log of S5 partition function will correspond to the free energy. So the S5 partition function is computable in the IR gauge theory via localization techniques. So I don't really have time to review these localization techniques, but via localization, the integral, the path integral on S5 actually localize. So the contribution of this path integral can be first modeled by this matrix model. So these are eigenvalues of this matrix model, and this quantity will depend, will be free field contribution of the matrix of the 5D theory reduced on S5, and this will be instanton contribution of the 5D theory, where R is the radius of S5. And the value of this integral localizes on some saddle points. So this is like basically standard law of localization. And so one needs to find the saddle points, and the saddle points will be, so the eigenvalues at these saddle points will be given by, so we scale like this, where beta is a positive number. This is for the grid, for like n D5 intersecting M-5. And in this limit, we can see if we take a large n limit, we can take the CFT limit, so sending the coupling to infinity. So we can send this quantity to 0, which tells that the coupling is infinity. But when we send like n or m to infinity, this means that this is infinity. And we can see that we can ignore the instanton contribution because they are weighted by this effective coupling. So the instanton contribution don't really contribute in this large n limit. What this implies is that now we can use just a free field description. And from the free field description, we can compute this limit. And this matches with the holographic quantity. So we need to compute the holographic quantity. So how do we compute the holographic quantity? Well, the holographic quantity was computed by evaluating the shell action of type 2B supergravity on this background, so on these solutions. So let's take again the grid, for example. So in general, this integral will be proportional to this quantity, where I0 is the integral on sigma of f of a function of these two holomorphic functions. This is generically what happens. And for the grid, it was computed in this paper, and the value, the large n value of this integral is given by this quantity. So we see that it scales like n squared and m squared. But still, naively, this integral will be infinite because we have the volume of ADS6. So we need to somehow regularize this volume, and this is done by the procedure which is called the renormalization, holographic renormalization. Similar to what I described yesterday for computing the dual of the A file anomaly. So in this case, the computation is quite clear. So we need to, for example, weak rotate ADS6. So we have a Euclidean ADS6, which is an S5 vibration over this. So where U is going from 0 to infinity. And in order to regularize, we take a cutoff which tells that the coordinate U can go from 0 to the sinh of 1 over epsilon. And then we integrate the volume of ADS6, which would be proportional to the volume of S5 times this quantity. And this quantity is as this following power series plus other divergent term. So epsilon goes to 0, of course. And then we have a finite contribution. So this infinite contribution are cancelled by some covariant counter terms that one can add in ADS6. So you can add like covariant tensor in ADS6, and you can cancel these divergences. But this is a universal piece which remains. And it's a universal contribution. So this universal contribution is given by this. Yes, 6. So now by plugging this formula into this quantity, what we get is exactly this match in this case. So this is a good test of ADS-CFT also for this ADS6 solution with the CFT pair, which in this case was the grid, but it has also been tested in other for other solutions. So, and with this, I conclude the lecture of today, and I leave you with some exercise. So thank you for listening.
So thank you very much, Fabio, for the great lecture. So we have time for some questions.
Can I ask a question?
Yeah, please.
Fabio, so in this geometry that you talked about in type 2B a couple of slides ago, that's due to this web of D5 and S5. Are there supersymmetric submanifolds where supersymmetric probranes can wrap, apart from the D1 and the F1 you mentioned?
Sorry, can you repeat?
Yeah, so in this you have this geometry like ADS6 fibered over Riemann surface and S2.
Yeah.
Right, and you mentioned about this supersymmetric probranes coming from F1 or D1. That's due to local operators. Are there other supersymmetric probranes in this geometry, which would correspond to defects rather than local operators?
Yeah, there are plenty. For example, you can wrap D3 branes, you can wrap NS5 branes.
So are there something that would correspond to a half BPS codimension defect? Because that's allowed by the superconformal algebra F4.
Yeah.
So what kind of, I mean, it should wrap the ADS5 sector, and it will also extend along the circle on your Riemann surface?
Yeah, you can wrap, I think you can wrap D5 branes. Like you can wrap, for example, if you have the grid, you can wrap NS5 branes connecting D5 branes. So instead of the strings, you just substitute the strings with the D5 branes or NS5 branes.
Let me make sure. Oh, I see. So that's the one cycles you're talking about. Okay.
That's the one cycle. Yeah.
So both D5 and NS5 will give rise to different kind of codimension defects, you're saying. So that's, I see. That's interesting. And for this, oh, sorry. Okay, can I ask one more question?
Yes, please, go ahead.
Right, and for this, so the local operators that you consider coming from graph the D1 and the F1 strings, do bound states between, bound state or PQ type ever matter, or they're just not PPS with respect to your configuration?
So it seems that my connection is not great. I don't know. Can you repeat one again? Sorry about that.
Oh, it's all right. Yeah, I just meant that. So when you mentioned this matching between the local operators, the protected local operators coming from probe ranks like F1 and D1s, does the PQ type strings ever matter, or they're just not supersymmetric in your setup?
PQ. Well, it depends on the fiber rings. So they need to connect the poles.
That's right.
So,
but for the particular case you consider, they do not contribute to the PPS spectrum?
Yeah, they do not, because they need to connect the pole. So.
Right. Okay.
Yeah.
Thank you.
I think they do not contribute.
More questions?
Yeah, can I ask a question?
Sure.
So just curiosity. So are there other manifolds apart from S5 on which the FFD localization works? And can you do this matching for something like, I don't know, I have in mind like squashed spheres or lens spaces in the lower dimensional cases?
Yeah. Squash sphere is allowed. You can do the matching in a squash sphere. I think there are a couple of papers about that as well.
And another question is if you can put, sorry?
You can also do S1 times S4.
Okay.
Yeah, sorry, I interrupted you.
No, okay. And another question is, I guess you can put an orientifold and have like alternating SO USP groups and does something similar works as well?
Yeah, although the solution might look more complicated. But yeah, you can definitely put orientifold.
And this has been done?
Like the match?
Yes.
I don't know. This might be a good discussion question. I'm not sure it has been done for like general orientifold. Yeah. So just in
type 2A, there are some examples.
Yeah, with those 7 planes, I agree. There is this paper. I don't know how general it is. So these are solutions. Sorry.
Oh, sorry. I just meant that in the type 2A case, the theory engineered by D4, D8, and O8 planes that correspond to USP to engage theory coupled to antisymmetric and and fundamental matter. Those cases, the holographic theory is known and has some singular locus, but you can do similar matching.
Yeah.
You can match the penetration function. You can also match the operator spectrum.
Yeah. And it also has
right, but it's true that the solution is tricky because of the singularities.
Yeah, but the plane singularities are still fine, as long as you have that marker. I mean, it's not really that you're at the singularity all of the O plane.
Right.
It's a manifestation of the O plane. It's not really the singularity of the plane, at least for this.
I have another very basic question, if I can ask.
Sure.
Is there any way to have more than 2 flavor nodes in a 5D linear quiver?
Yeah, I think so. Okay. Yeah, it's like you can have all sorts of flavor. You can have like a flavor on each. It's, I mean, in that sense, if you start from the end, like SUN configuration with 2 SUN flavor, it's very similar to 6D. You can have all sorts of, like important. So if you move in the X branch of those theory, you can have all sorts of quiver.
Because in this example that you presented, seemed to me that you had the flavors at the very top and very end, and then by successive Anani-Witten transition, you were bringing the flavor inside. So I was curious if you can have, you can start with 3 flavor nodes or more. But, okay.
Right. Well, you can get free. So if you like send out, that was a very specific example of sending some of the subwebs corresponding to D5, stretch between 2D7 to infinity. But you can send, you can do other other configurations, and other configuration that we change the quiver. So other configuration means that the D7 brain will enter into the web in other position, maybe also in different position sometimes. And if they enter in different position, that will correspond to different flavor symmetry for different age groups.
I see. And qualitatively, for each of these cases, you will have a monodromy cut ending on the 7 brain inside your brain web.
Yeah.
Okay.
I mean, the monodromy cut will be also outside, but if it's like at infinity. But when it's inside, then it changes the the angle of the web. So that way, it's like really contributing.
Okay. Thank you very much.
Okay. Any more questions? Okay, so let's thank again Fabio for the really beautiful lecture. So I remind you, tomorrow there is this, tomorrow at 9 a.m. Eastern time, there is this session for further question. Otherwise, I don't know if the other organizers have communications. I can, no. So I think I'll see you tomorrow.